designed based on the rigidity. Rigidity is nothing but deflections. Rigidity blindly we can say as a deflections. Okay. So before starting this one, I want to show one. Just I want to show one video. Okay, wait.
Is made up of multiple individual. Torsion is the twisting.
Noise is hearable. This noise, whatever
Yes,
the
sir.
voice is there.
Yes, sir.
Of an object caused by a moment acting about the object's longitudinal axis. It is a type of deformation. A moment which tends to cause twisting is called torque. A common example of an object subjected to torsion is the transmission shaft, which is used to transmit power by rotation. This could be the drive shaft and axles, used to transmit power from the engine of a car to the wheels, for example, or the shafts used to transmit power from the blades of a wind turbine to its generators. Let's explore what happens when we apply torque to a circular bar. We can see that the applied torque causes the bar to deform by twisting. An interesting thing we can observe is that individual cross-sections of the bar do not get distorted by the twisting. We can imagine that the bar is made up of multiple individual discs, which rotate relative to each other when the torque is applied, but do not deform. This is only true because the cross-section of the bar is axis symmetric. A bar with a rectangular cross-section is not axis symmetric, and so torsion results in warping of the bar cross-sections. This warping is complex, so in this video we will keep things simple and only consider torsion as it relates to circular bars. Let's fix our bar at one end, and track how a line between point A and point B deforms as we apply a torque to the other end. The applied torque causes the free end of the bar to rotate by an angle phi. This is called the angle of twist. It varies linearly from 0 at the fixed end of the bar to phi at the free end of the bar. We can calculate the angle of twist using this equation. It is a function of 4 parameters: the length of the bar L, the applied torque T, the shear modulus G, which is material property, and J, which is the polar moment of inertia. So, what is the polar moment of inertia? It defines the resistance of a cross-section to torsional deformation, due only to the shape of the cross-section. The polar moment of inertia for a hollow bar, with an outer radius RO and an inner radius RI, can be calculated using this equation. Setting the inner radius to 0 gives us the equation for a solid bar. One neat thing about the equation for the angle of twist is that it gives us a way to determine a material's shear modulus G experimentally. If we apply a known torque to a bar of known length and cross-section and measure the resulting angle of twist, we can use that information to calculate the material's shear modulus G. Torsion generates stresses and strains within the bar, which we need to be able to calculate so that we can make sure our bar won't fail. To figure out how to calculate these stresses and strains, we can start by observing how a small rectangular element on the surface of our bar deforms. The element is initially rectangular, but when the torque is applied, it gets distorted. Let's take a closer look. Because the bar is axis symmetric, we know that individual cross-sections will rotate but won't get distorted. So the sides CF and DE of the element will only move vertically along the lines shown here. After the torque is applied, the angles of the element are no longer 90-degree angles. This gives rise to a shear strain, which corresponds to the angle you can see here. We can calculate the shear strain by considering only the geometry of the bar in the deformation. It corresponds to this angle between AB and AB prime. We can use trigonometry to derive an equation for shear strain. For small angles, gamma will be approximately equal to the tangent of gamma, which makes it equal to the length BB prime, divided by the length AB. AB is the length L of the bar. We can calculate the length BB prime by realizing that it is the arc length of a circle with a radius r, covering an angle equal to the angle of twist theta. So the shear strain is equal to the radius of the bar multiplied by the angle of twist divided by the length of the bar. This is actually only an equation for the shear strain on the surface of the bar. But what about inside it? It turns out that the shear strains increase linearly with the distance from the center of the cross-section. So if we define ρ as the radial distance from the center of the cross-section, we can replace r in this equation with ρ to give us an equation we can use to calculate shear strain due to torsion at any point within the bar. That's shear strains covered. But what about shear stresses? Like the shear strains, shear stresses increase linearly with the distance from the center of the cross-section, with the maximum shear stress occurring on the outer surface, as you can see here. This is true for a solid bar, but also for a hollow bar. This is useful to know because it means that hollow bars are way more efficient at carrying torsional loads, since the central part of a solid bar is only resisting a small part of the total load. Let's consider a small element within our cross-section that has an area equal to dA and is located at a distance ρ from the center of the cross-section. The internal force acting on this element is equal to its area, dA, multiplied by the shear stress τ. We can use this information to work out an equation for calculating the shear stresses. The moments caused by the internal forces acting on all of the elements within the cross-section must sum up to be equal to the torque T. Otherwise, equilibrium is not maintained. We can represent that mathematically by this integral. We know that the quantity τ divided by ρ is a constant, because the shear stress varies linearly with the distance from the center of the cross-section. So we can rearrange the terms and move τ over ρ out of the integral. It turns out that the integral we now have on the right is actually the definition of the polar moment of inertia, so we can replace it with the letter J, and we can rearrange this to get an equation for shear stress. The shear stress is a function of the torque T, the distance ρ from the center of the cross-section, and the polar moment of inertia J. It's quite a simple equation. So we now have equations that allow us to calculate the shear strains and shear stresses. We also have the equation for angle of twist that we talked about earlier. These three equations tell us everything we need to know about a circular bar which is under torsion. So far, we have only talked about a uniform bar fixed at one end with a single applied torque, but shafts are often loaded by multiple torques. This shaft, for example, which is supported by bearings at both ends, is driven by a gear at point B, and in turn drives two gears at points A and C. It is loaded by 3 torques. Before we can use the equations for shear stress, shear strain, and angle of twist that we just developed, we need to figure out the internal torque at each location along the shaft. The process for doing this is similar to calculating the shear force along a beam, which I covered in a separate video. First, we draw a free body diagram. Then we make imaginary cuts and use the concept of equilibrium to determine the internal torque at different locations along the shaft. This will give us an internal torque diagram that looks something like this. The maximum shear stress will occur in the section of the shaft with the largest internal torque, and can easily be calculated using the equation we derived earlier. I want to end the video by talking about failure due to pure torsion. If we have 2 bars, one made of a ductile material and one made of a brittle material, and we apply the same torque to both bars, we will observe that they fail differently. The ductile bar fails at an angle perpendicular to its axis, but the brittle bar fails at a 45-degree angle to its axis. We can explain this by remembering that ductile materials tend to fail in shear, and so fracture along the plane of maximum shear stress. but brittle materials are weaker in tension than in shear, and so tend to fracture along the plane of maximum tensile stress. Moore's circle for pure torsion looks like this. We can see that when our stress element is oriented this way, the shear stresses are at their maximum values, and we have no normal stresses. There is a 90-degree angle on Moore's circle between maximum shear stress and maximum normal stress, which means that normal stresses are at a maximum when our stress element is rotated by an angle of 45 degrees. This explains why brittle and ductile materials fail in different ways due to pure torsion. That's it for now. Thanks for watching, and don't forget.
So this was a video for understanding from the beginning to last this rigidity. Okay, so see here. So design of shaft based on the rigidity. Rigidity is nothing but here deflections. Okay, so in shaft you can find the deflection two types. One is a torsional deflection when it is rotating. Angle of twist you can you observed in the just video angle of torsional means deflection through the angle, that is a torsional rigidity. And deflection of shaft is laterally means when the shaft is subjected to the tensile force, means at two ends it is subjected to tensile force, or at the two ends of the shaft it is subjected to compressive. Otherwise when shaft is supporting in two bearings and gates or other pulleys, just you have seen in the video, so gates are mounting. So because of that reason the shaft is going to subject to the lateral deflection, because when it is going to rotate at high speed. Okay, so such kind of failure we need to overcome, that is the design of shaft. Just what previous topic what we discussed about the failure of the shaft in the strength criteria that we overcome. Okay, that we overcome based on the design strength criteria. So strength criteria is twisting moment and bending moment, combination of these two, and additional direct load, we are direct load acting on the shaft. So these four categories are the based on the strength criteria. So that we overcome and we solve the some empirical relations. That empirical relations are going to use in the problems, and we are going to calculating the safe dimensions for the shaft. So same likewise here also, whatever the deflections are generating through the shaft, that deflection we need to overcome. Okay, now first one is a torsional rigidity. Torsional rigidity also we can call as a torsional deflection. Okay, so this torsional rigidity in general, it should not exceed the theta value. Here torsional rigidity means it is totally discussing about the theta value here, torsional deflection or angle of twist. Okay, so the theta value in general should not exceed the 1 degree per meter length. It should not exceed the, see here, it should not exceed the 1 degree per meter length, means it is a limited value for the general shaft. Okay, and this torsional rigidity is important. Torsional rigidity is an important term for the camshaft designing. This torsional rigidity is important design in the camshaft. This camshaft generally we are using in a IC, our two-wheeler engines, our four-wheeler engines, our train engine, whatever the IC engines are there, in internal combustion engine, in that camshaft are we are using. What is the use of camshaft? This camshaft are going to operate the valves, operate the engine valve to intake stroke and outlet outward stroke, and whatever the total operations are going to completing in the four-stroke engine, whatever the valves are open, at what time valve is going to open, at what time valves are going to get closed, at what time the valves are going to again open for exhaust stroke, these are all going to place with the help of camshaft. Okay, this camshaft is going to rotate with the help of timing gates, with the help of timing gates which is attached to the flywheel. Okay, so this camshaft is going to design based on this torsional rigidity. Okay, for this camshaft the value is given, the theta value should not exceed the 0.25 degree per meter length. For this cam shaft, 0.25 degree per meter length it should not exceed. Okay, remember this value. For the cam shaft, theta value is 0.25 degrees. And generally in line shafts, whatever the line shafts there, line shafts are there, line shaft means throughout cross section it should have the uniform cross section. Okay, so for that the angle of deflection is theta should not exceed the 2.5 to 3 degree per meter length. Okay, 2.5 to 3 degree per meter length. And this value we can also calculate with the help of this torsion equation, T by J equal C theta by L or G theta by L. So remember this terminology. T is the torque or twisting moment and J is the polar moment of inertia. Okay, this polar moment of inertia is according to the cross section we need to select. Here we are discussing about the shaft. So pi by 32 d power 4 for solid. If it is hollow, so d naught is the diameter of the total shaft. Okay, so this is the solid shaft, this is the hollow shaft, and G is the modulus of rigidity of material, and L is the total length of the shaft. So this is the equation, theta equation, that is a torsional rigidity T into L by J into G. Okay, with this relation we can calculate the torsional rigidity. Okay, so sometimes theta value is we are assuming like this 0.25 degree or 2.5 to 3 degree or 1 degree we are assuming. Okay, sometimes the question is asking what is the torque, sometimes the question is asking what is the length of the shaft, sometimes the question is asking what is the modulus of rigidity. So you should remember the theta value when the problem is asking other than this theta. When the question is asking other than the theta, to find the t value, otherwise L value, otherwise G value. So if you have the remembrance, if you put the value of the theta value here, easily you can get the remaining values. Okay, so this is the theory about the torsional rigidity. The next one is the lateral rigidity. Lateral rigidity means, just you have seen in the video, shaft is fixed between the two bearings and gates are mounted on the shaft, isn't it? So in that case, if the shaft is rotates with high speed, because when power is while the power is transmitting, the shaft is going to rotate with high speed. At that time, what happened? Because of center of gravity, center of center neutral axis of the shaft is going to change. Okay, because of the mountings, whatever the presence on the shaft, and when the shaft going to rotates with high speed, there will be definitely the shaft is going to subjected to deflection laterally. Laterally, the shaft is going to subjected deflection. Okay, so here the transmitting shaft, the transmitting are in place. This design for the transmitting shaft is mainly used for the lateral rigidity. In previous case, for the designing of the camshaft, torsional rigidity is important one. Now, for the transmission shaft, lateral rigidity is very important. Okay, because the shaft or pulleys or whatever are there mounting on the shaft, because of imbalancing of the gears or pulleys, the shaft is going to vibrate laterally. Okay, because of the imbalancing of the shaft, gears and pulleys. Okay, when the shaft is going to rotate with high speed, the lateral deflection or lateral vibration is going to taking place. Okay, so these deflections already you have studied in the strength of material subject. If it is simply supported beam, what is the deflection? If it is like cantilever beam, what is the deflection? Okay, that equation are going to use here. And one more thing is, because the cross sections means shaft is having the circular cross section general, when the shaft is having the square cross section, we don't know that equation. Okay, when the shaft is having the triangular section, what is the deflection, we don't know. We didn't study in the strength of material subject. So that reason general equation is there in strength of material. One general equation is there, that is d square y by dx square is equal to m by ei. Based on this equation only, you have solved the number of equation in the strength of material. For simply supported beam, for the cantilever beam, for the fixed beam, whatever the deflections and slopes are there, that all are things you calculated with the help of this equation. Here also this equation is going to play a vital role to calculate the deflection, lateral deflection, nothing but lateral vibration you are going to calculating here. Okay, and this is a bending moment. M is a bending moment, E is the Young's modulus, I is the area momentum of inertia, phi is the lateral deflection, shows this one. Okay, so this is the total synopsis, total theory regarding the design of shaft. So from the next class onwards, we are going to uh, discuss about the problems. Okay, we have the 10:06. We have the time. We are going to solve some few problems. See, this is the one. Is there any doubts you have regarding the theory topic? If you don't have any doubt, we'll start the solving the problems. If you have any doubt, you can ask. Otherwise, we are going to start the problems of the design of shaft. Okay. So first one is I am starting the problem. Here, a line shaft is there, rotating 200 RPM and transmitting the So a line shaft is rotating 200 RPM and it is transmitting the 20 kilowatts, and shaft is maybe assumed as a made of mild steel. So here remember, concentrate on the what is appearing, concentrate on the type of material using here. Okay, type of material, because some here the question is mentioning shear stress is given as a 42 megapascal. So don't need not to select the assumption, because of the shear stress is given in the problem. Sometimes only material type will be given like a mild steel and the shear stress value is not given. So based on this material, you need to consider the material properties. Okay, so should concentrate on the type of material. Okay, shear stress is given 42 megapascal, asking to calculate the diameter of the shaft, neglecting the bending moment. Okay, neglecting the bending moment. Now, to calculate the diameter of the shaft, first check the problem belongs to which category, because design of shaft having the based on two criteria, your shaft is going to designing. Based on the two criteria, the shaft is going to designing. First one is the strength wise, second one is the deflection wise. Okay, the first one is strength wise. So strength wise, again four categories are there. So see here, the power is transmitting 20 kilowatts and shear stress is given, and running at a 200 RPM is given. It means this is totally based on the strength wise. It is based on the total strength wise, because the power is given and shear strength value is given 42 megapascal and speed is given as a 200 RPM. Okay, based on these three parameters, we are concluding that this is the based on the strength wise. Again, strength wise, we have four type designs. What are those? Pure bending, pure torsion, combination of pure bending, combination of bending and torsion, and fourth one is the additional axial load applying. In that four, this problem belongs to which one? Four categories are there in strength wise. In that strength wise four category, the given problem belongs to which one? Which category means? See the here material property is given, shear stress value is given. Shear stress as a 42 megapascal. So based on this statement, we need to conclude the given problem based on the pure torsion. The given problem is belongs to pure torsion. Okay, so pure torsion, what is the equation is there to for the solid shaft? One relation is there, one is torque T equal pi by 16 into sigma s into E cube. Okay, so this is the torque transmitted by the shaft. So here question is asking to calculate the diameter of the shaft. Here not mention it is hollow or it is solid. So that reason I am taking the, it is a solid shaft. Okay. Now D, what is the D here? D is T into 16 by pi into sigma s, pi into sigma s. Cube root of T into 16 by pi into sigma s. Okay. So 16, pi value, and sigma s is a 42 megapascal is given in the question. Now, one unknown parameter is a torque. So we need to calculate additional here torque value. So see the given data transmitting the 20 kilowatts and it is having the 200 megapascal. So it is power equation, we know power equal to pi nt by 60, 2 pi nt by 60. Okay, this is in terms of watts. Okay, this is in terms of watt, but here question is given kilowatts. Okay, with this relation we can calculate the T value. What is the T here? T equal P into 60 by 2 pi n. Okay, so substitute the P value here as 20 kilowatts is given. 20 kilowatts means we need to write the kilo value also, 10 to the power of 3. 10 to the power of 3. N value is given in the question as 200. N value is given in the question 200 rpm. Now let me tell what is the T value, torque value. What is the T value here? Tell me the T value. Make it fast. P value 20 into 10 cube. N value is 200. Tell me the T value. T value 954. Very good. 954. 954. 954. Okay. What is the units? Units are very important. What is the units here? Newton meter. Very good. 954 Newton meter. Substitute this value here in this equation. This T value in this equation. Okay. You will get the. So before substituting kilowatts, okay, Newton meter, convert this Newton meter into mm, because so otherwise you could first calculate the D value, you will get the answer in terms of meter. Okay, that we need to convert into mm. Okay, tell me the D value. Cube root of T into 16 by pi into sigma s. What is D value? That is D value. Make it fast. You don't have time. D value 48.74 mm. Very good. 48.7 mm. Okay. Is it right for all? Is it right for all?
Yes, sir.
Okay. So before starting the problem in design of shaft, first read the question properly. Means the question given question belongs to which category? Means strength wise or deflection rigidity wise. After deciding the strength wise, after deciding the rigidity wise, again it is belongs to which category again, because in strength wise four categories are there, in rigidity wise two categories are there. Okay, in strength wise four categories, the given problem belongs to again belongs to in the four, whatever the four categories are there in strength wise belongs to which one. Like that you need to first analysis, you have to do the analysis. After analyzing first, after analyzing whatever the parameters are required to solve the problem regarding to the four different categories. Okay, so like this you need to solve the problem. So this is the one of the problem according to the first category of the strength one, that is the shaft is subject into the pure torsion. Okay. So today I'm going to upload the whatever the PPT so far we have discussed the designer shaft. This total PPT recording in the MS Teams and go through that once, whatever the equations are there. And additionally, you need to remember the moment of inertia equations and polar momentum of inertia equations, because without remembrance of the equations we cannot solve the problems. Equation in the subject, equations are going to play the vital role here. Don't focus on the theory in the subject, don't expect the theory out. Okay, only the problems and derivations are the important for the subject point of view. Okay, and theory you can expect for the 2 marks only, that's all. Means how many short answer questions are there? 10 short answer questions are there. Okay, for the 10 short answer questions, how many marks will you get? Maybe 20 or 25, isn't it? So for that reason, please concentrate on the derivations and equations and problems.